Well, good afternoon, everyone, and thank you, Anna, for the introduction. Of course, thank you, Vicente, for letting me to be here. So I'm going to talk about different projects that we have developed at Universidad Miguel Hernández de Elche about the development of brain-machine interfaces for interacting with robotics exoskeletons. What is the goal? The goal is to try to improve, the current rehabilitation therapies that are being used with people that have suffered some kind of neurological conditions, such as, for instance, a stroke or a spinal cord injury. So before starting with my talk, let me show you where we are. We are located in Elche. Elche is in the south of Comunitat Valenciana, and we are very close to Alicante. And we started to develop, brain-machine interfaces like 20 years ago. First of all, we started to understand how the brain is working, how we can decode the brain in order to perform some kind of, control of external devices without moving any muscle. For instance, you can see here in this video, in this picture, that we started to control, for instance, industrial robots in order to perform some kind of pick-up-place task, but only by commanding the robot by using the brain signals. I mean, without controlling any kind of interface, physical interface. And after that, we realized that maybe we could use all this knowledge in order to command, wearable robots. I mean, if we can decode the brain signal, what we can do is we can try to control robotic exoskeletons in order to help people to walk or, for instance, to move their arms. So in my talk, I'm going to focus on this kind of brain-machine interfaces that we have developed for controlling lower limb exoskeleton. So, which is our motivation? Our motivation is this one. I mean, there are multiple neurological conditions that can affect the gait. For instance, when a person has suffered a stroke, the person maybe can recover the gait, but is not going to walk in a natural way. We are going to check, for instance, in this video, that people can walk, of course, but they are not walking on a natural way. So what happens when a person has suffered, for instance, a stroke? Well, what happens is that they follow a motor rehabilitation therapy. And usually, they follow what is called a bottom-up approach. I mean, basically, imagine that the person has suffered a stroke, and the problem is on the brain of the person. So there is, for instance, the motor cortex has been affected, and the person cannot walk in a natural way. So in that case, what people do is this kind of rehabilitation when there are some people moving physically the legs of the person in order to try to promote the neuroplasticity that has been lost on the brain. I mean, imagine the problem is on the brain, but we are not acting on the brain. We are acting on the legs of the person in order to try to promote the neural mechanisms. In this picture, in this video, you can see that there are 3 people for performing the rehabilitation. 2 people that are physically moving the legs of the person, and another one that is assuring the stability of the user over the treadmill. So as you can imagine, this is quite hard for everyone, and the cost is also important. And a lot of time, the task is very repetitive, is to move the legs all the time of the person. So, fortunately, in the last year, different kind of robotics exoskeletons have appeared. You can see here several examples. All of them are focused on lower limbs. I mean, they are helping people to walk around. But this kind of technique, this kind of machine, can be used for, helping people to rehabilitate. I mean, because in the end, they are moving the legs. There is not people moving the legs of the person, but there are robots that are actually moving the legs of the person. But in the end, we are following this kind of traditional rehabilitation, this kind of bottom-up approach. We are not acting on the brain level. Indeed, these devices are generally commanded by physical interfaces. For instance, you have to press some button if you want to go to start the gate or to stop the gate, or even in some cases, you have to shift your body in order to start the gate. But in the end, what we are doing is the same, therapy. We are moving the legs of the person in order to try to promote the neural mechanism that have been lost. Well, what we think in our lab, in the brain-machine interface systems lab, is that we could improve, the current rehabilitation therapies by combining brain-machine interfaces and combining robotics exoskeletons. A brain-machine interface is a system that is collecting the brain signals in order to process them and in order to know if the person wants to walk, the person wants to stop the gait, the person wants to move their arm, etc. But in the end, we need to collect the brain signals. And in our case, in our lab, what we are doing is we are collecting the brain signals by using, electroencephalography. It's a non-invasive technique. It's there is any harm for the user. But in the end, what we are doing is, we are collecting the brain signal, and you can see here, and we are doing a kind of bypass in order to know if the person wants to start the gait or to stop the gait. For instance, if you want to start the gait, what we do is we send a command to a lower-limb exoskeleton in order to physically starting the gait. Okay? So what we have introduced is this kind of new top-down approach, because now, if the person wants to walk, there is nobody that is physically moving the leg of the person, but it's the arm user who is sending a command to the legs. How? Because he has to think, or she has to think, about moving their legs. Okay? So we are combining this kind of traditional rehabilitation, this kind of bottom-up approach, with this new top-down approach. We are doing both at the same time. And we think that this is going to be better for the rehabilitation of the user. We are going to promote better the neuroplasticity. So I'm going to show you two projects where we have done this, where we have developed different kind of brain-machine interfaces for trying to help people to recover from some kind of stroke or spinal cord injury. The first project is the Walk project. This was a project that we ended in 2022, and it was a project that we did in collaboration with several centers. We collaborated with the main hospital in Spain for paraplegics, that's in Toledo, and also we collaborated with a hospital in Asturias, and we also collaborated with the University of Houston. What was the idea? The idea was to develop a brain-machine interface in order to command, the movement of a lower limb exoskeleton. So basically, the idea was, if I want to walk with the exoskeleton, I have to be thinking all the time about moving my legs. So while the brain-machine interface is detecting that I am thinking about moving my legs, the exoskeleton is being moved. But as soon as I relax, the exoskeleton is stopped. So basically, that's the idea. But for doing that, we needed to implement two different kinds of brain-machine interfaces. One that is used when the person is in the static condition. When the person is in the static, is stopped, he has to think about the motor imagery in order to start the gait. Okay? And we implemented another different kind of brain-machine interface for the moving condition. I mean, while I'm working with the exoskeleton, I need to be thinking again about moving my legs in order to command the exoskeleton, because if not, the exoskeleton is going to be stopped. So let me explain you this with more detail. So in order to do that, we needed to calibrate two different kinds of brain-machine interfaces. And for doing that, we need a lot of training for each user. Indeed, what we did is 5 sessions during consecutive days. I mean, every day we perform one different session when, first of all, we collected a lot of signals from the users in order to train our models. So first of all, what we did is, we are going to train the model that is used when the person is in static. The person is not moving. In this case, first of all, the person was relaxed during several seconds, and we were collecting all the EEG signal. And after that, we said to the person, now you have to be thinking about moving your legs. You are not going to move your legs. You are going to think about that. And we were collecting all the signals. And after that, we repeat again the process. And we did that 10 times. So in the end, we were collecting a lot of signals in order to have enough data in order to train our model. And we repeated the process, in this case, when the person is actually moving with the exoskeleton. So the person was wearing the exoskeleton. The person, first of all, was relaxed, although the exoskeleton was being moved. And after that, while the exoskeleton was being moved, the person also thinking about moving his legs. And finally, the person was again relaxed, and we were collecting all the EEG signal. We have to do this for each user every day in order to train the system, because if not, the user is not going to be able to use, the exoskeleton with the brain-machine interface. Well, I'm not going to get into a lot of detail, but I have to say that basically for doing that, what we did is we collected 27 electrodes, 27 EEG signal from the motor cortex area, basically. And we extracted the main feature of the EEG signal, and after that, we use a very simple machine learning technique in order to, classify if the person was thinking about motor imagery, was thinking about movement of the legs, or if the person was relaxed. So after that we train the system, we have, the VMIs with all the models calibrated, the person can use the system. And for doing that, the person, first of all, is relaxed and is using this brain machine that we have adjusted during the static condition. So the person needs to think about walking. And as soon as the person starts to think about the movement of their legs, what we do is actually we activated the exoskeleton, so the exoskeleton starts to walk, and we go to the other brain-machine interface. And in this case, if the person is thinking all the time about moving his legs, the exoskeleton will be moved. But if the person is relaxed, we will stop the exoskeleton. And we repeated this process, in this case, 5 times per user. So let me put you now one video of one of the experiments that we did with one spinal cord injury patient at the Hospital for Paraplegics in Toledo. The video has sound. I hope that the video can be heard. Basically, the person is, I don't know if we can hear the sound. No. Okay, anyway. Basically, the experimenter has said the person, imagine that you are moving your legs. So the person starts to think about the imagination of walking. And as soon as the VMI detects that, we send a command to the lower limb exoskeleton, so the lower limb exoskeleton starts to walk. Okay? You maybe have checked that suddenly the exoskeleton has been stopped. This is because maybe, the brain-machine interface has not detected that the person was thinking about that, or maybe it was because, the person has not think about that. Anyway, we checked that the person was in charge of his rehabilitation. I mean, the person was capable of walking because the person was thinking about movement of their legs. So now there is nobody that is physically moving the legs. Now he's moving his legs because he wants to move his legs, and he's sending that command by using their brain signal. As you can see here in this video, there are several people assisting the experiment. I mean, there is a person behind the volunteer that is assuring the stability of the exoskeleton, and also there is another one that is, assuring the stability of, this kind of scratches. But this is also because it was a requirement by the hospital. So it would be possible for the user to use the system with the brain-machine interface and the exoskeleton. Anyway, we checked that the person can use the system, but we realized that it was quite difficult for him to be all the time thinking about the motor imagery in order to, assure that the exoskeleton is being moved. So we started a new project, that is the project Regate, that we are going to finish this project next month. And it's a project where we have tried to improve, the accuracy of the decoding, and we have tried to implement a brain-machine interface that can be used in an easier way by, the volunteer. This is a project that we are also doing in collaboration with the Hospital for Paraplegics in Toledo and the University of Houston and the Hospital of Asturias. And also, in this project, we have incorporated the Institut Guttmann in Barcelona. So what is the idea? One of the things that we did in this project is to change the paradigm for commanding the exoskeleton. I mean, in the previous case, as I have told you, what we needed to do is all the time to be thinking about moving our legs if I want to command the exoskeleton. But this is not what we do. If I want to walk, I don't have to be all the time thinking that I want to walk. So basically what I do is, okay, I send a command to start my gait, and when I want, I stop my gait. So we implemented a new kind of brain-machine interface where we are going to do that. So basically what we did was, okay, I am here in this kind of line that we have put over the ground. So you can see that there are some yellow line, red line. So the yellow line is the line when the person has to think about starting the gait. But as soon as the BMI detects that, the exoskeleton is automatically activated. So the person doesn't need to be all the time thinking about the motor imagery. But, as opposite, we need to stop the exoskeleton. And when the person reaches this kind of red line, the person needs to think about stopping the gait. So when if I want to stop the gait, I need to think about stopping the gait. So this was a different versus the previous paradigm that I have shown you before. So in order to do that, what we did is we implemented a different kind of machine learning technique. Now we implemented a deep learning model when we were collecting the data of all the users. I mean, in the previous one, we implemented, we calibrated with the specific data of each user his specific or her specific model. Now we don't do that. What we do is we are still doing 5 sessions, but now in the first session, we don't do anything related with the training, and we don't do anything related with the use of the lower limb exoskeleton. In this case, what we do is basically to explain the experiment to the user, okay, to get familiar with the devices, etc. But in session 2 and 3, we perform, the training. We try to calibrate the deep learning model. And for doing that, what we did is we perform 7 trials when the person is static and 7 trials when the person is in movement. When the person is in static, we have to do as we have done in the previous project. The person has to think about being relaxed, or the person has to think about moving his or her legs. And for the motion model, we have to do the same, but in this case, the skeleton is all the time moved. I mean, it's externally moved, not because the person is thinking about that. So after collecting all that signal, what we did is, in the last 2 sessions, we performed, again, 14 trials in order to get data for adjusting, the models. But in this case, we perform a fine-tuning of all the layers of the model per user and per session. And finally, what we did is, in session 4 and 5, we tested the system. I mean, after calibrating the system, we performed the experiment in closed loop. So let me show you one video of one of the experiments that we did. In this case, you can see here, this is our lab. You can see here that there are some marks. Maybe you can see better that there is a red mark here. Here is a green one. So it means that in the green one, the person has to think about starting the gait. So the person starts to think about that, and as soon as the BMI detects that, the person doesn't need to be thinking about that. The person is relaxed, and the exoskeleton is being moved. But when the person reaches the red line, the person needs to think about stopping the gait. Okay? So now the person is in charge of all the situation, because in the previous project, the person needed to hear some kind of instruction from the experimenter. Now, no. Now is an asynchronous paradigm when the person can control if he wants or she wants to start or to stop the gait. Anyway, here you can see the result of the decoder. In green, we are showing the accuracy for starting the gait. So in most cases, always the person is capable of starting the gait. But in red, you can see the accuracy for stopping the gait. Now, there is not possible always stopping the gait. But this is not the, the worst problem. the worst problem is shown in blue. That is the ratio of stops. This is the proportion of successful stops versus the number of total stops. So it means that in some cases, the exoskeleton is being stopped not because the person wants to stop the exoskeleton, but because the algorithm is not working well. So we needed to think about changing these VMIs in order to improve this accuracy. So what we did is to implement an additional brain-machine interface that is based on the error-related potential. What is this? The error-related potential is a potential that is produced on the brain when we realize that something is not working properly. Imagine, for instance, that you are wearing your EEG card with a lower limb exoskeleton, and you start to think about starting the gate. And you see that the exoskeleton is not being moved. So in that way, this kind of brain potential is produced on your brain. And we can put electrodes for detecting that. And if we detect that, we can change the output of the algorithm and say, no, I want to move the exoskeleton, so the exoskeleton starts. What is the problem? Imagine that now you don't want to start the exoskeleton, the movement of the exoskeleton, and suddenly the exoskeleton starts to move. The same kind of error potential can be produced, and you can detect that. But of course, the problem is that the exoskeleton has been already activated. So in order to avoid that problem, what we did is we introduced some kind of visual or some kind of interfaces that have to be activated before sending the command to the exoskeleton. In that case, we use a pair of glasses with some lights and some kind of vibrator, for the wrist. So basically, the idea was, okay, imagine that I'm working with the exoskeleton, and suddenly, the lights are activated and the vibrator are activated. It means that the VMI is on the verge of stopping the exoskeleton, but you don't want to do that. So in that case, the kind of error potential is produced, so you can send that command because you are performing a kind of self-tuning of the brain-machine interface. So we are correcting the output of the brain-machine interface thanks to detecting this kind of error-related potential. Well, let me show you one of the video of one of the experiments that we did, in this case, in Institut Guttmann in Barcelona. Now we are using a different kind of robotic exoskeleton. In this case, it's a robot from Hokoma. It's actually working over a treadmill. So now the person needs to be thinking about, the gait and that, but the person cannot walk. So you can see here that there is a screen when the person can see the advance of the user during his or her walking. So I'm going to put the video. So basically now the person is moving, and we want to stop the gait of the person. So a red line is going to appear, and we are going to check that the person is not able to stop the exoskeleton. But this kind of error potential has been produced because the person has realized that something is not working properly. So we detect that, and we send a command to the exoskeleton in order to stop the exoskeleton. That way, we can improve the accuracy of the system. Well, so let me say several things related with the experiment that we have done. First of all, we have verified that people with motor limitations can use brain-machine interfaces for interacting with robotics exoskeletons. I mean, we have done experiments with spinal cord injury people, with stroke people, and all of them are able to command the robots using their brain signal. And we think that this is going to be better for their rehabilitation because we are introducing this kind of top-down approach that is combined with the traditional rehabilitation approach, this kind of bottom-up approach. But, and this is very important, we need to perform more clinical trials in order to check the clinical relevance of this technology. Because maybe we are developing, a very fancy technology, but this is better or not than moving the legs of the person. We have to perform clinical trial in order to check if it is worth to use this technology or not. So that would be all. Let me thank you before ending to my lab, that they are actually doing the hard work, and here doing the easy work, that is to talk. So let me thank my team, and of course, all the sponsors of the research. Thank you. I don't know if we have time for questions. No, you have time for questions, so if any of you have any questions, okay, perfect. No, tranquilo, don't worry.
Thank you, Miguel Juan. My question is, are there any similarities between the signals produced by one person and other person through the BMI to control the exoskeleton, or are they totally different? And if they are similar, is there the possibility to train the person to emit precisely the signals that are going to work?
The problem is that they are different, but they are different even for the specific user depending on the time when they do the experiment. So there is a lot of variability on the signal, and that's a big problem. Yeah.
And would that be solved changing the kind of signals that you are looking for, like or using a different type of sensors, like maybe intrusive sensors or something like that, so you can be more precise?
You could be more precise if you, for instance, you will use, invasive electrodes, because that way you can put the electrodes in some specific area related with motor cortex, and you can even be able to detect the activation of some group of neurons. But what we are checking now, that now with non-invasive technique, we can do things that maybe 20 years ago were only able to do people that was working with invasive technology. But of course, that would be easier for, detecting the signals and that.
Thank you.
Thank you.
Hi. So first of all, thank you very much, José María, for that interesting presentation in a so interesting topic. I wanted to ask, as far as I know, with EEG technology, it's possible to detect more than just one command. And my question is that one: why are you just getting the start or stop command when, for example, you could get like move left leg or move right leg command? Wouldn't that be more realistic? Thank you.
Yeah, thank you. Thank you. Well, it is very difficult to detect more than one command, but it depends on the application. I mean, here I have been talking about, imagination of the legs. The legs are represented, or the motor cortex, just in the middle of both hemispheres, so just in the inner part of the brain. So it means that when you are putting the electrodes over the cortex area, you are receiving, the signal with a very poor quality. But for instance, if you want to detect, if you are thinking about imagination of your right hand or your left hand, that's easier, because you have the representation over the top part of the motor cortex. So that's the main problem. Anyway, if you increase the number of classes that you want to detect, you are going to decrease the accuracy of the system. So in the end, you have to reach a trade-off between accuracy and number of classes.
Thank you.
Thank you.
Hello. Well, first of all, thank you very much for this speech. It was quite interesting. But I have a question. What is the possible scale and impact of this technology globally, like in different sectors?
I mean, of course, the clear impact is in rehabilitation of people with motor limitation. I mean, I have to say that there is an economic problem related with that. I don't know if your question is related with that, because, I mean, for instance, lower limb exoskeleton the cost of this kind of devices are around 100,000 euros. You have to add the equipment for, collecting the signal in the end, you have to spend more or less about 120,000 1,000 euros per device, no? So that limits, the potential, expansion of the technology. But the important thing is not that, but, the strategy. Because now there are people that are producing very cheap EEG devices. Of course, you cannot collect 27 electrodes, but you can collect 8 electrodes. And for instance, you can use lower limb exoskeletons that are not gonna, allow you to walk, but maybe they are gonna allow you to move your ankle, for instance. So, and that's gonna be a lot cheaper, I mean. So, of course, that is the more potential application of the technology, from my point of view, the clinical one.
Okay. So yeah, I was wondering whether it could be in different sectors apart from rehabilitation, like in sector of defense, for example, or in sector of companies that help people to move from house to house.
I mean, for instance, exoskeletons have been used, in the army in order to, to resist, more and that, and even, for instance, in factories, in factories of cars and that, they are using exoskeleton in order to help them, and specifically in order to avoid to get some kind of illness related with heavy things, no? But in that case, you don't need the brain-machine interface. I mean, it's only the technology related with the exoskeletons.
Okay, thank you very much.
Thank you.